Okay, so let's continue with our discussion of Fourier series. From last time, for a given function in L2, we define the Fourier coefficient f hat of n to be the integral 1 over 2 pi minus pi to pi f of t e to the minus I n t dt, which up to a factor of 1 over root t is equal to the inner product of f with e to the I n t over square root of 2 pi in the Hilbert space L2. Okay? And the question that we had, and we also had that the nth partial sum for the Fourier series associated to f was given by sum from n equals minus n to n, f hat of n e to the I n x. And the question which we're trying to resolve is, do we have for all f in L2 limit as n goes to infinity of f minus Sn of f2 equals 0. Okay? All right. In other words, is f equal to its Fourier series, at least when we interpret equals as in this sense here. Now, based on what we've done for Hilbert spaces, this question is equivalent to the following statement. If f is in L2, and the Fourier coefficients are all 0, does this imply f equals 0, right? So this question is, by what we've done for Hilbert spaces, big L2 is a Hilbert space. This question here is equivalent to this statement, which is that the collection of orthonormal vectors in big L2 consisting of the exponentials divided by square root of 2, is this a maximal orthonormal subset, or as we, or using the terminology we had from last time, does that form an orthonormal basis? So this is the statement that we're going to prove this class. And we're going to proceed via kind of Fejer's method, if you like to give it a name, where what we did last time was, you recall, we had the Cesaro Fourier mean. We defined to be the average of the first n partial sums, with the hope that somehow this behaves a little bit better than the partial sums, because that's the thing we're trying to study, and that's a hard question. And typically, means of sequences might behave better than the sequences themselves. But if the original sequence converges, then the means converge. So we should expect this to converge to f, but hopefully faster or have better, more recognizable properties than just studying the partial sums directly. And we'll get to in the next statement why it's a little bit clear why the Cesaro Fourier means converge to f. And so what our goal, what we're going to show is that f is in L2, then the Cesaro Fourier means converge to zero. Converge to f as n goes to infinity. Okay? And so once we've proven that, then that gives us what we want in the yellow box, right? That proves what's in the yellow box, because let's take a f in L2 with Fourier coefficients all 0. Then all of the partial sums will be 0. Then all of the means will be 0. And since the means converge to f, that proves f is 0. And we get what's in the yellow box. And therefore, the partial sums, the partial Fourier sums converge to f as capital N goes to infinity in L2. All right? And then once we prove that, I'll make a couple of comments about other types of questions one can ask and what you can do. Or brief comments. So this is our goal for this lecture. And we should be able to get through it. Okay, so let me first rewrite the Cesaro Fourier means slightly differently, sort of how we did in the previous lecture for the partial Fourier sums. We wrote them as what's called a convolution. I haven't defined convolution, but an integral of a function depending on x and t times f of t dt. And we're going to do the same now for the Cesaro means, and we'll see here in what it's a little bit more clear, although I didn't talk so much about the Dirichlet kernel that appears for these guys, but why the Cesaro means converge to f. Okay. All right, so the statement is for all f in L2 minus pi to pi, we have that the nth Cesaro mean of f, or Cesaro Fourier mean, I can write as the integral from minus pi to pi of a function kn of x minus t times f of t dt. So remember, for the partial sums s sub n, we could write it as d sub n, where d denoted the Dirichlet kernel, where kn of x, this is equal to n plus 1 over 2 pi, and then 1 over 2 pi times n plus 1 times sine n plus 1 over 2x over sine x over 2 squared, and this holds at x equals 0. This one holds at x not equal to 0. Okay? And this thing we call Fejer's, or the Fejer kernel. So, all right. And now let me just list off a few properties that we'll get from this. Moreover, we have the following properties. One, Kn is non-negative. Kn of x is equal to Kn of minus x. It's even. And Kn is 2 pi periodic. The second is that the integral of k sub n of x from minus pi to pi dx, or let's make this t, dt equals 1. And the third is if delta is a positive number less than pi, less than or equal to pi, then for all x with absolute value bigger than or equal to delta and less than or equal to pi, we have that Kn of x, which is equal, I don't need the absolute values because it's non-negative, is less than or equal to 1 over 2 pi over n plus 1 times sine squared delta over 2. Okay? So let's prove this theorem, and then I'm going to say a few comments about, well, since I have these properties right here, let me go ahead and make a few comments before we prove it. What does that mean Kn looks like? That means, let me draw 0, pi, minus pi. So Kn is non-negative, it's even, and away from a small neighborhood, it's quite small if capital N is very big. So what it's looking like is, maybe the first one, and it's kind of large at the origin. Okay, so maybe that's n equals, let's say 1, and then let's say this is delta, and then minus delta. If I were to now look at, let's say n equals, I don't know, 1 billion, it looks more like something that's very concentrated at the origin, okay? But in such a way that the area underneath the graph, so the integral, the area equals 1. Okay, and the same with, what I drew in white, because white was supposed to be n equals 1, yellow was supposed to be n equals, 1,000. The area is always 1. Okay, so what is this? So this is telling you that if I look at sigma n of f, so this is just some remarks, this is not to be taken completely literally. This is just kind of the intuition on why we believe that the Fourier, or that the Cesaro means converge to f, and then I'll say how this picture differs from if we looked at just Sn. So, this means that sigma n of f is, in fact, so remember, we're going to get in the end that this is equal to Kn of x minus t, f of t dt. Now, Kn is very concentrated near where t equals x. Okay? So based on the picture, as n gets very large, this thing is getting more and more concentrated near where n equals x. Okay? Now, and therefore, at least for, let's say, very nice f, if this thing is concentrated near where t equals x, then f of t will be approximately f of x. So f of x comes out of the integral, because this is an integral dt. So since this thing is concentrated at, and because the area underneath the curve is always 1, this integral is always equal to the integral of Kn over any, so Kn is 2 pi periodic. This integral is equal to the same integral over any 2 pi periodic interval, which means I could put here, I could add an x to both top and bottom, and therefore change variables to get, this is Kn of t dt, which equals, because the integral is 1, I would get something like f of x. Okay, so this is kind of a heuristic reason on why one should expect why one should expect the Cesaro means to converge to f. Okay? Okay. Now, if you look back at the kernel that we had for the partial sums, right, it had kind of some of the same-ish properties. It was 2 pi periodic and also even. The integral was 1, and it did kind of decay away from 0. However, it's not non-negative. I'm talking about the Dirichlet kernel dn, which if you look back in your notes was like sine of n plus a half times x over sine x over 2 with a constant out in front. And that little difference, that the fact that this kernel is non-negative and the Dirichlet kernel is not, makes kind of a big difference. So although this heuristic argument, maybe you don't see it there in the actual proof itself, that oscillation, and what I mean by oscillation is the fact that dn actually does oscillate between negative and positive values. This bit of oscillation is actually what you can use to build up a continuous function whose partial sums do not converge to that continuous function at a point. Okay? But as we'll see, for the Cesaro means, the Cesaro Fourier means, basically pick a space and the Cesaro sums or Cesaro means converge to the function in whatever space you're talking about. And I'll say a little bit more about that in a minute. But okay, so let's prove the theorem that the Cesaro means are written in this way, and the kernel has these 3 properties. Okay. So let me recall that we have Sn of x, or let's put a k there. This is equal to, as we wrote last time, minus pi to pi dk of x minus t, f of t dt, where dk of, let's see, t was from last time equal to 2n plus 1 over 2 pi at t equals 0, and sine n plus a half t over sine t over 2, and then with 1 over 2 pi out in front, I believe. Let me make sure I got the right exponent. Right. For t not equal to 0. Okay? Oh, and this should be k. Okay. So using this, we have that the Cesaro sum of x, this is equal to 1 over n plus 1, sum from k equals 0 to n, the mean of the first n partial sums. And this is equal to, now skf of x is equal to this, so I can write this as integral from minus pi to pi of 1 over n plus 1, sum from k equals 0 to n of dk x minus t f of t dt. And so this here is kn of x minus t. All right, so now I'm just going to verify that kn of x takes that form that we had before. And kn of x, this is equal to 1 over n plus 1, sum from k equals 0 to n of dk of x. And let's go to the next half board. So I can write this as 1 over 2 pi n plus 1 and times, so I will look at the case that x is non-zero. X equals 0, you'll get what you get, but let's look at x not equal to 0. So then I plug in this formula here and pull out sine t over 2 or sine x over 2 squared on the bottom, and then I get k equals 0 to n of sine x over 2 times sine n plus 1/2 x. Okay? And because I feel like it, we put a 2 here and a 2 here. Why do I feel like it? Well, it's because if I have 2 times sine of A sine B, I can write that as using my angle sum formulas from trigonometry. You wondered why those would be useful. Well, here they are, appearing in the advanced MIT class. You can write this as sum from k equals 0 to n of cosine nx minus cosine n plus 1x. Let me make sure I got that right. Or this should be k, I'm sorry. That should have been k. 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 All right? Now this is a telescoping sum, right? I have a sum of cosine kx. I have a cosine k plus 1x. So this is equal to so let's just write this out. And let me just indicate why this is a telescoping sum. We get cosine 0x minus cosine 1x plus cosine 1x minus cosine 2x dot 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 plus the last one, which is cosine nx minus cosine n plus 1x. And okay, so this telescopes, that cancels with this, that will cancel with so on, and that last one will cancel. So all that we're left with is this one minus this one divided by this 2 that I have right there, and I get 1 over 2 pi n plus 1 times 1 over sine squared x over 2 times 1 minus cosine n plus 1 x over 2. And again, using trig formula, 1 minus cosine 2a equals sine squared, divided by 2 is equal to sine squared a. So I get this is equal to 1 over 2 pi n plus 1 times sine squared n plus 1 over 2 x divided by sine squared x over 2. Okay? Okay, so that verifies the formula for the Fejer kernel. What about the properties that we have there? These properties, at least the first two, kind of follow directly from this formula and the definition. So one follows immediately. This is clearly non-negative. It's even. Taking taking x to minus x does not change this because we have squares, and also because of the squares, it's 2 pi periodic rather than 4 pi periodic. Okay. Okay. So that's 1. For 2, we note that if we take the integral from minus pi to pi of the Dirichlet kernel, this is, okay, we had a formula for the Dirichlet kernel, but remember, this is nothing but, this was defined to be the sum from n equals minus k to k of e to the I n t dt. Okay? Now, e to the I n t, when n is not equal to 0, is 2 pi periodic. And when I integrate it from minus pi to pi, the integral from minus pi to pi of this 2 pi periodic thing, you can just check. I mean, it's the integral of sine nt and cosine nt over its period. That's going to give me 0. So all I pick up is when n equals 0, right? And so that's equal to just the n equals 0 term, so that gives me 1. Okay? So since the integral of each Dirichlet kernel is 1, then the integral of the Fejer kernel, which, remember, this is equal to the average of the Dirichlet kernels. And each of these is 1. Sum from k equals 0 to n, 1, I get n plus 1. Divided by n plus 1, I get 1. Okay? So that gives me 2. And for the third property, for the third property, we have, what do we have? Then the function sine squared x over 2, this is, what does it look like? This is increasing. I should say it's even. And increasing on 0 to pi. So what it looks like is sine squared x over 2. So there's pi minus pi. Sine squared looks like kind of goes up to 1. So if I'm looking at all x outside of, so in that kind of shaded region, then if x is outside of delta, this delta region, then I get that sine squared x over 2 is going to be bigger than or equal to whatever, so it sits above the value that I get here, which is sine squared delta over 2. And therefore, I get that kn of x, which is equal to its absolute value, is less than or equal to 1 over 2 pi n plus 1 sine squared n plus 1 over 2x over, I had sine squared x over 2, but since sine squared x over 2 is bigger than or equal to sine squared delta over 2, taking 1 over reverses the inequalities, and I get sine squared delta over 2 here. Sine of anything is always bounded above by 1, so I get this is less than or equal to 1 over 2 pi n plus 1 sine squared delta over 2. Okay? So, for the moment, let me put this absolute value there. I'm not doing it because for a specific, I think it looks better. It's because I'm going to make a comment in a minute. Okay. Let me just make a small comment. Well, let me prove the next theorem, and then I'll make the comment. Okay, so we have these properties of the Fejer kernel, and now what we're going to do is, on our way to proving that we have convergence of the Cesaro means to a function in L2, we're first going to do it for continuous functions. So you proved in the assignments that in L2 minus pi to pi, the continuous functions vanishing at the two endpoints are dense in the space big L2. Okay? Now, if a function's continuous and equals 0 at both of the endpoints, it's 2 pi periodic in the sense that it equals, it has the same value at both endpoints. And therefore, the subspace of continuous functions that are 2 pi periodic is dense in L2. So, if we're going to be able to show that the Cesaro means converge to a function in L2 for arbitrary L2 function, maybe it makes sense to try and do it first for continuous functions. And it's there that kind of this argument that I just kind of, this heuristic argument I gave here will be more math-like. Okay, so we have the following theorem due to Fejer. Which is the following: if f is continuous and 2 pi periodic, meaning f of pi is equal to f of minus pi, then not only do we have the Cesaro means converging to f in L2, we actually have it in sort of the best sense that you could for a continuous function. Then sigma n of f converges to f uniformly on minus pi to pi. Right? So before we're looking at Fourier series in L2, so convergence in L2 was kind of the way one makes sense of infinite series or something converging to something else, right? If we're looking at continuous functions, then we have a different norm there, right? If we want to just consider a complete space containing continuous functions, we have the uniform norm or the infinity norm. And so what this says is that even in this smaller space and in this stronger norm, we have convergence of the Cesaro means to the function f, okay? But again, this doesn't imply that the Fourier series converges to F uniformly. Like I said, one can, in fact, use this oscillatory behavior of the Dirichlet kernel to prove there exist continuous functions whose Fourier series diverges at a point, okay? And therefore it doesn't converge uniformly to the function. All right, but this is true for the Fejer kernel, or the Cesaro means, because of these properties of the Fejer kernel, because it has this kind of shape where it's non-negative, it's peaking near the origin, and it has total mass 1, a total integral 1. In some sense, you should think of as n goes to infinity, sigma n is looking more and more like the Dirac delta function at 0, which maybe you encountered in physics. If that doesn't mean anything, don't worry about it. Just skip to the next part of the talk. But which is supposed to have this magical property that it's 0 away from 0, which these are kind of looking like, has integral 1. And when you integrate it against a function, you get f evaluated at the origin, which is kind of like what we're saying here. Okay, so that's, again, that's some more heuristics. But, you know, linear operators that, depending on a parameter, that appear like this, where it's a function of this form times f of t integrated dt, pop up all the time in harmonic analysis, okay? And having these properties, in fact, pops up also in harmonic analysis, okay? Harmonic analysis being a fancy name for Fourier analysis and other stuff. Okay, so let's prove this. So the first thing that I want to do is, so f is a continuous function on minus pi to pi that's 2 pi periodic. So I can extend f to all of r by periodicity. In other words, so we extend to all of r. Meaning I have, so there's pi, minus pi, pi. Here's 3 pi. Here's minus 3 pi. So supposedly I have this continuous function, which is 2 pi periodic. Now I take that continuous function and just extend it by how it is here. And so on. Okay, I'm not saying I extend it by 0 outside. I'm saying I extend it periodically. Okay? Okay. Now I can write down a formula for exactly how you do that, but just trust me, you can do that. And also the following simple properties, then f, this now referring to it as kind of a function defined on all of r that's 2 pi periodic, this is also continuous, is 2 pi periodic, and which implies that f is uniformly continuous and bounded, i.e., if I look at the infinity norm of f, first off, because by periodicity, this is just equal to sup xn minus pi to pi. And because f is continuous, this thing is finite. Okay? All right. Now, it's not difficult to believe that f is, if I extend it by periodicity, periodicity, it's going to be continuous. But using that and the fact that it's 2 pi periodic, you can then also conclude that it's uniformly continuous. Okay? Meaning, let's just quickly review what uniformly continuous means. This means for all epsilon positive, there exists a delta positive such that if y minus z is less than delta, then f of y minus f of z is less than epsilon, meaning I can choose a delta independent of y and of the point, right? Continuous at a point means I fix x, then for all epsilon there exists a delta. Uniformly continuous means the delta doesn't depend on f. I mean on x, on the point that I'm looking at. All right, so we have those. There's that basic observation that we're going to make there, and maybe I'll just leave this up for now. Okay. So we want to prove f converges, or the sigma n's converge to f uniformly on minus pi to pi. So that means we should be able to find for every epsilon a capital M, such that for all n bigger than or equal to m, sigma n, and for all x in minus pi to pi, sigma n of f minus f is less than epsilon in absolute value. All right, so let epsilon be positive. Since f is uniformly continuous, as I stated in the recalling the definition, that implies that there exists a delta positive such that if y minus z is less than delta, then f of y minus f of z is less than, and let me get this right so it comes out pretty in the end, is less than epsilon over 2. Okay? So now what we're going to go through is make that argument, which I just erased, actually precise. All right? So here we're saying if f is very close to, if any 2 points are sufficiently close, f is going to be close in value. Okay. Now choose m, natural number, so that for all n bigger than or equal to m, the quantity twice times the L infinity norm over n plus 1 times sine squared delta over 2 is less than epsilon over 2. Okay, so n plus 1, that's the thing that's changing. So I have these fixed numbers here now. I've fixed delta. I have the L infinity norm of f. So I have this number here, and I'm just saying choose a capital M so that for all n bigger than or equal to m, this number times, and I'll even put it here, times 1 over n plus 1 is small, is less than epsilon over 2. And I can do that because this, as capital N goes to infinity, converges to 0. Right? Okay, now since f and k sub n, the Dirichlet kernel, are 2 pi periodic, I can write the Cesaro mean, which is given by minus pi to pi, kn of x minus t, f of t dt. I can make a change of variables, set tau equal to x minus t, and then this will be equal to what is it going to be equal to? X minus pi, x plus pi, kn of tau, f of x minus tau d tau. Okay. All of this change of variable stuff is fine because I'm dealing with continuous functions. I'm integrating continuous functions, so that's the Riemann integral. We have change of variables for the Riemann integral, so that's completely fine. Okay, now this is the product of two pi periodic functions, and if I take the integral of that quantity of a 2 pi periodic function, that's the integral of that is equal to the integral over any interval of length 2 pi. All right, so we're integrating over an interval of length 2 pi. Right, we're going from x minus pi to x plus pi. That is equal to the integral of the same quantity over any interval of length 2 pi. So it's also equal to the integral over minus pi to pi. Okay, so all I'm saying is I can change variables and move the x minus t, and let me even go back to t instead of tau here. Because of periodicity, I can switch this x minus t over here to f. Okay? All right, now we're going to start seeing some magic happen. And this is where that heuristic argument that I gave earlier actually starts to make sense. So then I have that for all n bigger than or equal to m, so I have that condition that quantity was less than epsilon over 2. And for all x in minus pi to pi, I have that sigma n of f, sigma n f of x minus f of x. So this is equal to minus pi pi. And again, I'm going to write this now as kn of t f of x minus t dt minus. Now, here's the trick. The Fejer kernel has integral 1, so I can actually write f of x as minus pi to pi integral kn of t times f of x dt. I'm integrating dt. Right? Then this just pops out. I get f of x times the integral of the Fejer kernel, which is 1. Okay? And this equals minus pi pi. So just combining things, kn of t f of x minus t minus f of x, which is good because we have a continuous function, and now we have something inside that looks like I'm subtracting f of some argument minus f of the argument minus something. Okay? Now, I'm going to split this integral into two parts and then use the triangle inequality and bring the triangle inequality inside. In fact, I'm going to go ahead and do that here. This is less than or equal to if I combine terms like I did and then bring the absolute value inside. Okay? And now I'm going to split this integral up into two parts. This is equal to the integral over t less than delta. And because kn is non-negative, this is just kn of t f of x minus t minus f of x dt plus the other term. Okay? Kn of t f of x minus t minus f of t dt. All right? Now, what do we know? If the absolute value of t is less than delta, then x minus t minus x is equal to minus t, which is an absolute value less than delta. So note that x minus t minus x equals t is less than delta here, right? And therefore, this quantity here is less than epsilon over 2 by how we chose delta. So this is less than epsilon over 2 times the integral over this region of kn of t. Okay, but I can make this region larger and just go back to, so well, let me just leave it here as it is. Plus, now what do I do with this piece? I have this I bound by twice the L infinity norm of f. The absolute value of this is less than or equal to, by the triangle inequality, the sum of the absolute values, which is less than or equal to the sup of this plus the sup of that in x, which is equal to the twice the infinity norm. So I get 2 times the infinity norm of f popping out from this term, and kn of t, I'm away from t less than delta, and this is where I use that third property that I have from before, that it's less than 1 over 2 pi. So let me leave this here. Sum 1 over 2 pi n plus 1 sine squared delta over 2 dt. Okay? And now this I can say is less than or equal to the whole integral over minus pi to pi, which is equal to 1. Plus, again, making this an integral over the entire region, I get 2 pi times, or divided by 2 pi gives me 1. So I get twice infinity over n plus 1 sine squared delta over 2. And we chose n plus 1 so that this second quantity here is less than epsilon over 2. Okay? And therefore, uniformly, we proved that for all capital N bigger than or equal to m, for all x in minus pi to pi, the difference in sigma n f and f is less than epsilon, proving uniform convergence. Okay? So here's the remark I was going to make. Is that the same proof can be modified if instead of kn of x being bigger than or equal to 0, let me make sure I'm saying the right thing. So if instead of this property, which we had for the Fejer kernel, we have that sup over n of the integral from minus pi to pi of kn of x is finite. Meaning, if I have a function, or if I have a sequence of functions, kn's, and I have the corresponding, operators that look like that, maybe they're not associated to any questions about Fourier analysis, but I'm just saying. And it satisfies the 3 properties I had before, with the exception of being non-negative, but instead of that, it satisfies this property. Then I can redo the same proof and show that those things converge to f uniformly. Okay? Why am I saying that? Because maybe you would like to then try your hand at replacing kn with dn, the Dirichlet kernel. Okay? The Dirichlet kernel satisfies all of the other properties we had up there. The integral is 1. In absolute value, it kind of decays away from x is less than delta, and it's even in 2 pi periodic. Okay? But it doesn't satisfy this. That if I look at minus pi to pi of the Dirichlet kernel. What one can prove is that this is something like log n for large enough n. Okay? All right. So that was just a tiny remark I wanted to say on why, if you thought about maybe redoing this proof using the Dirichlet kernel, which satisfies almost all the same properties, with the exception of being non-negative, you could if the Dirichlet kernel satisfied this bound, but it doesn't. It satisfies this bound. It's like log n, and therefore if I take the sup, I don't get something finite. Okay? All right, so we've proven that the Cesaro means of a continuous function converge uniformly to a continuous function. So we're almost to the point where we can say that the Cesaro means of an L2 function converge to an L2 function and conclude that the subset of exponentials divided by square root of 2 pi form a maximal orthonormal subset of L2 and therefore is an orthonormal basis, so that the partial Fourier sums converge back to the function in L2. We just need kind of one more bit of information. So we have the following theorem. For all f in L2 of minus pi to pi, if I look at sigma n of f, so first off, this is just a finite linear combination of exponentials, right? So this is clearly an L2. It's a continuous function. But if I take the L2 norm of that, it could depend on n, but in fact, it's less than or equal to the L2 norm of f. Okay? So how we'll prove this is we'll first, and this bound is what allows us to go from the 2 pi periodic continuous functions to general L2 functions by a density argument. Okay? So first we'll do this for 2 pi periodic continuous functions, and then by density conclude it for L2 functions. So suppose first that f is 2 pi periodic. And then, of course, extended to R by periodicity like we did before. Then, as before, we had that the Fejer mean, the Cesaro mean of f is equal to the integral from minus pi to pi of f of x minus t, kn of t dt. And so if I compute the integral sigma n f of x squared dx, this is equal to, so each one of these is equal to an integral over minus pi to pi, so I'm going to have 3 integrals. And f of x minus s times the complex conjugate f x minus t times kn of s and kn of t, and then d s dt dx. Okay? Now, all these functions are continuous, so we have Fubini's theorem, which says we can reverse the order of integration however we please. So I can write this as the integral from minus pi to pi of now integrating first with respect to x. Kn t, and now integrating first with respect to x. dx, let's say ds dt. Okay? Now, I do Cauchy-Schwarz on this. And so this is less than or equal to minus pi to pi, pi, kn of s, kn of t, times, I'm using Cauchy-Schwarz in x now, so times the L2 norm of the function minus s. So I'm taking the L2 norm in this variable. 2 times 2 ds dt. Okay? What I mean by this is I'm taking the L2 norm of this function depending on s, but in the first variable, in this x variable. Okay? So just write it out to see what I mean. Now, this is the integral of a function over an interval of length 2 pi that's 2 pi periodic. That's equal to the integral of that function over any 2 pi periodic interval, or any interval of length 2 pi. So I can, in fact, remove this s and remove this t, and just pick up the L2 norm of f in both places. So this is, in fact, equal to, and because these two things no longer depend on s and t, they come all the way out of the integral, and I get L2 norm squared times minus pi to pi, n of s ds times the integral from minus pi to pi, n of t dt. Both of these integrals equal 1, so I get norm squared. And I started off with the L2 norm squared, or the L2 norm squared of the Cesaro mean of f. So I get this for all 2 pi periodic continuous functions. Okay? Now, how do we then get the bound for general f? We use a density argument. So by what you've done in the assignments, there exists a sequence of 2 pi. So let me start over real quick. Now let's take a general element in L2. Okay, now we start by assignments. You know that there exists a sequence of 2 pi periodic continuous functions converging to f in L2. Fn of 2 pi periodic continuous functions such that Fn, the Fn's converge to f in L2. And one can verify simply from the definition of each of the Cesaro means that then, so this is as little n goes to infinity, that then the Cesaro means also converge as little n goes to infinity. So capital N here is fixed. Okay? Just using the definition of what the Cesaro mean is and Cauchy-Schwarz, basically. Okay? And the fact that Fn's converge to f in L2. Thus, we get that the L2 norm of the Cesaro mean is equal to the limit as n goes to infinity of, so this is little n, of the L2 norm of the Cesaro means of these continuous 2 pi periodic functions, which, as we've proven already, these are all less than or equal to the L2 norm of Fn, because they're 2 pi periodic, and again, because f is converging to Fn, the norms converge. and I get the result I wanted for general L2 functions. Okay, so now we're almost there. What we have is this bound, and we have that the Cesaro means converge to, so if I take the Cesaro means of a continuous function, those converge to the continuous function uniformly on the interval. We're going to use that, this bound, and the density, again, of the 2 pi periodic continuous functions in L2 to conclude the following theorem. For all f in L2, the Cesaro means converge to f as capital N goes to infinity. In particular, we get as an immediate corollary if all of the Fourier coefficients are 0, then f is 0, right? Because if I have this, if I've proven this, and all the Fourier coefficients are 0, then the Cesaro means are all 0. And therefore, since this is 0 converging to f, f must be 0. Okay, and therefore, the set of exponentials, normalized, of course, form a maximal orthonormal subset of L2, i.e. that they're a orthonormal basis for big L2, which answers the question we had about Fourier series converging to a function in L2. Okay. All right, so we'll do this just as a standard or epsilon n argument. Let epsilon, so let f be in L2. Let epsilon be positive. So we know that let G, we know that the continuous 2 pi periodic functions are dense in L2 because you did this in the assignment, that for any f in L2 over an interval, I can find a continuous function that vanishes at the endpoints and therefore is periodic, which is close to f in L2. So there exists a G that's continuous, 2 pi periodic, such that f minus G in L2 norm is less than epsilon over 2, or epsilon over 3. So since sigma n G converges to G uniformly on minus pi to pi, there exists natural number m such that for all n bigger than or equal to m, for all x minus pi to pi, I have that sigma n g of x minus g of x is less than epsilon over 3 square root of 2 pi. Okay. Now we go about the part where we replace f with g. Okay. Then for all n bigger than or equal to m, if I look at the L2 norm of sigma n of f minus f in L2, and I apply the triangle, I add and subtract terms and apply the triangle inequality, I get that this is less than or equal to sigma n of f minus g L2 plus sigma n of G minus G in L2 plus G minus F in L2. Okay? So sigma n of F minus G is equal to sigma n of F minus sigma n of G. So I kind of use that there without explicitly stating that. So let me say sigma n of F minus sigma n of G. Just from the definition, you can check this is equal to sigma n of F minus G. Okay? Now, by the bound I just proved, the L2 norm of the Cesaro mean is less than or equal to the L2 norm of what of the function here. So this is less than or equal to F minus G, 2. And then I also have this L2 norm of F minus G there, so I'll put a 2 there, plus, and I'll actually write out what this is, sigma n G of x minus G of x squared dx 1/2. Okay? Now, F minus G is less than epsilon over 3, an L2 norm, so this is less than twice epsilon over 3. Sigma n G minus G is less than epsilon over 3 square root of 2 pi here. So I get square epsilon over 3. That pulls all the way out, minus pi 1 over 2 pi dx. And I just get epsilon in the end. Okay? Okay. So that concludes what I wanted to do for Fourier series, at least for now, which applies, what we've done for, Lebesgue integration, these big LP spaces, and also some of this general machinery we built up for Hilbert spaces to actually kind of answer a more concrete question rather than, just trying to prove general statements. I mean, general statements are very, very useful. I'm not saying they're not, but I'm just saying so that you can kind of see a concrete problem why one would want and use functional analysis in the first place. Now, coming back to what we've done so far, so let me just make a couple of remarks about what we haven't shown. It's a very deep theorem due to Carlson. So what we've shown is that the partial sums, so we showed the set of exponentials normalized or a maximal orthonormal set. I mean that they're orthonormal basis, so the partial sums converge to F and L2. So this is what we've shown. For all F and L2, the partial sums converge to F and L2, right? But this does not translate into a pointwise statement. This does not say that the partial sums converge to F almost everywhere. Okay, there is a general theorem one can say that is covered in more advanced measure theory classes, where one can say that there exists a subsequence converging to F almost everywhere, but that's not very good, or at least very clean. Now, for a long time, it was not necessarily believed that the partial sums converge to F almost everywhere, but a theorem due to Carlson shows that for all F and L2, partial sums do converge to the function almost everywhere. Okay, this is, in fact, I mean, maybe this is true, maybe this is not. I heard this from my advisor. Carlson spent a few decades trying to prove the negation of this statement, trying to come up with an example of a function whose partial sums don't converge almost everywhere back to the function. And then he came up with the bright idea that, well, maybe that's not true. Let me spend some time trying to put myself in the other shoes. And within like a year or a couple of years, he was able to prove this theorem. Okay, so this is Carlson's theorem that we do have convergence almost everywhere. Now you can also ask about, what about convergence? So this is convergence in L2 of the partial sums. We have other LP spaces, right? What about in those LP spaces? Can I replace this 2 with P? The Fourier coefficients and partial sums, these all make sense for any big LP space. So what is known is that also, and now the name is escaping me, but I'll just state it, for all P between 1 and infinity, the partial sums in LP, or the partial sums converge to the function in LP. When P equals 1, this is false. Okay? And when P equals infinity, this is also false, because the partial sums, these are a finite linear combination of exponentials and therefore a continuous function. Okay? So you can't have for an arbitrary function in L infinity, which can be discontinuous, it just has to be bounded, these converging to L and such a function, because this would have to be, because then the limit would have to be continuous. Okay? The uniform limit of continuous functions, which L infinity is kind of is, has to be continuous. Okay? So that's why you wouldn't expect it for L infinity, and for what one would call duality, because L infinity is the dual of L1, you also don't get P equals 1. But in fact, things are worse there. You can come up with an L1 function so that the Fourier series, I don't think I'm lying when I say this, but diverges almost everywhere, I want to say. Okay, I don't think I'm lying. But for P equals 1, one can come up with a example where the partial sums diverge pointwise almost everywhere. Okay. Okay, but to prove kind of this flavor of statements requires sort of deeper harmonic analysis. Harmonic analysis being the umbrella that Fourier analysis sits in. Okay, and requires a knowledge of, or at least working with certain operators, which are called singular integral operators, which were developed back in the last century, middle of the last century, at the University of Chicago, by my mathematical grandfather and great-grandfather, which gives you some beautiful results about, again, convergence of Fourier series, but also some applications to PDEs, which were why they were originally created in the first place, and so on. But perhaps you'll encounter that if you take a class in harmonic analysis or Fourier series. I haven't taught the Fourier series class, so I don't know what it's about. But that kind of material will not be covered in this class, and this will be as far as we go, as far as these types of questions. All right, so next time we'll move on to minimizers over convex, over closed convex sets, and consequences of that, which one being that we can identify, which is kind of the most important application, we can identify the dual of a Hilbert space with the Hilbert space, okay, in a canonical way. You can already kind of prove that. You can already prove that if you wish, using the fact that every Hilbert space is isometrically isomorphic to little L2. You know that the dual of little L2 is 1 over Q is LQ, where 1 over 2 plus 1 over Q equals 1, and therefore Q equals 2. So little L2 is a dual of itself. But we'll prove it for general Hilbert spaces, and which has some very important and interesting consequences when it comes to now studying, solving equations in Hilbert spaces, meaning you have linear operators. When can you solve equations involving these linear operators and so on? All right, so we'll stop there.